Our mission for this deep dive is to explore a really novel research paper. It's titled Efficient Hybrid Inference for LLMs, Reward-Based Token Modeling with Selective Cloud Assistance.
Okay.
And this paper, it promises a breakthrough in, well, blending the best of both worlds, trying to give you LM-level quality without, breaking the bank.
Which sounds like the Holy Grail in some ways.
It kind of does. So what's the aha moment here? Instead of making a full query decision like which model to use for the whole thing, imagine if an AI could decide token by token, whether it needs a bit of help from the cloud.
Okay, that's interesting. Very granular.
Exactly. So let's maybe start by digging a bit deeper into the core problem for you, the listener. We know LLMs are incredible, but as we just touched on, they're vast scale. Billions of parameters sometimes.
Yeah, huge models.
It demands huge computational power and memory resources.
Yeah.
And that pushes them onto expensive cloud infrastructure.
Which, of course, sends operational costs soaring for anyone trying to use them seriously.
Right. And what's fascinating is how previous attempts tried to bridge this gap.
Yeah.
These hybrid inference or routing approaches.
Yeah, like those proposed by researchers like Ding et al. Or Ong et al. The thing is, they were a bit of a blunt instrument.
How so?
Well, their limitation was that they would route entire queries to either an SLM or a cloud LLM based on how difficult they predicted the query to be.
So one decision for the whole interaction.
Exactly, an all-or-nothing decision. And while this did help reduce costs, it often led to, well, suboptimal performance, especially with more complex queries that really needed a mix of strength.
Okay, so it wasn't flexible enough for tricky stuff.
Pretty much. You lost nuance.
So given those limitations, how does this paper propose to tackle the problem differently? What's their core breakthrough that moves beyond that all-or-nothing approach?
So this paper introduces a really novel hybrid inference approach. It focuses on a reward-based mechanism that dynamically determines just how much the cloud LLM gets involved.
Okay.
Right there during the token generation process. The fundamental shift is this. Instead of the entire query being routed,
Right.
each token predicted by the SLM is evaluated against a reward score.
Each single token. Wow.
And only when this score falls below a certain threshold is the cloud LLM consulted for assistance in predicting the next token.
Ah, okay. So it's like, I'm not sure about this next word. Better ask the expert.
Exactly. It offers incredibly fine-grained control over cloud LLM involvement and truly enables selective assistance, just bringing in the heavy artillery precisely when needed.
So this isn't just about cost savings then, is it? This level of fine-grained control where a model essentially judges itself word by word, that opens up some intriguing possibilities, doesn't it?
It really does.
Who benefits most from this? Is it mainly about getting advanced AI onto everyday devices, or more for big enterprise applications?
I think it's potentially transformative for both, actually. This granular control means you can sort of dial in the exact balance of quality and cost for specific use cases.
Yeah.
Like imagine a smart assistant on your phone. It's generally handled by an SLM, keeps things snappy and local.
Right, low power consumption.
Exactly. But then it can seamlessly call on a powerful cloud LLM only for those really complex questions. Keeps costs down, but ensures you get high-quality answers when it really matters.
Or maybe for a small business.
Yeah.
Like running an AI chatbot without that huge continuous cloud spend.
Precisely. It really helps democratize access to LLM capabilities, I think.
That's remarkable. So how does this per-token intelligence actually work? Let's dive into the reward model. You said that's the brains behind these dynamic per-token decisions. How does it learn to make those calls?
It's quite clever, actually. The reward model's architecture, it's inspired by reinforcement learning with human feedback, RLHF.
Okay, yeah, familiar with that.
And it's trained using a technique called proximal policy optimization, or PPO.
PPO,
Yeah.
that key algorithm in RL.
Exactly. It helps models learn complex behaviors by making small, stable updates. In this case, its job is basically to assign a score to each token, telling us how well that token, generated by the SLM, aligns with the cloud LLM's probability distribution. Essentially, how likely the bigger model would have produced that same token.
So it's trying to predict the LLM's preference, not a human's.
That's the key distinction. And the selection of this reward model is absolutely critical. Ideally, it should be from the same family as the cloud LLM itself.
Why is that?
It just facilitates quicker and more accurate alignment with the desired distribution. Now, it needs to be lightweight for efficiency, like they used the Quinn 2.5B instruct model in their experiments.
Which is pretty small, relatively speaking.
Right, but it also needs to be sophisticated enough to accurately capture the larger LLM's complex distribution. If the model's too small, it might lead to unnecessary cloud calls or, maybe worse, miss those crucial moments when LLM assistance is genuinely needed. It's a balancing act.
Okay, that makes sense. Now, you mentioned RLHF, but unlike traditional RLHF, which often uses human preferences, this approach needs synthetic data sets. Why is that? Why not just use human feedback here?
That's a great question. It's because the goal here isn't to align the reward model with, like, human taste or general helpfulness.
Right, not about which answer sounds better to a person.
Exactly. It's specifically about aligning with the cloud LLM's probability distribution. They want the small reward model to essentially think like the big LLM, not like a human judge.
Gotcha. So they need data that reflects the LLM's own choices.
Precisely. So they create these synthetic data sets, often using methods like RLAIF, that's reinforcement learning from AI feedback, where LLMs themselves are used to label response pairs. It bypasses human annotation entirely.
Clever. Saves time and focuses the training.
And the data synthesis procedure they outline is quite detailed. First, you have model serving, basically running both the SLM and the cloud LLM, maybe using something like VLM.
Okay, that's an efficient serving engine, right?
Yeah, exactly. It's an open source engine designed to make serving large language models super fast and efficient, really optimizes throughput.
So they can generate lots of examples quickly.
Right. Allows them to efficiently generate a large volume of responses from both models. These then form the basis for the paired comparison dataset.
Where the cloud LLM response is good and the SLM response is less good.
Generally, yes. The cloud LLM response is typically designated as chosen, and the one from the SLM as rejected for that comparative training.
And within that response generation, I read they introduced a very clever trick, didn't they? Something about handling the length of the responses.
Ah, yes, that's really interesting. Instead of just using fixed length sequences, the responses are chunked into segments of variable length.
Variable length, like how variable?
Could be anything from a single token right up to the minimum length of either the SLM or the LLM responses in that pair.
Wow, down to a single token. Why is that so important?
Well, it's key because it directly addresses a common issue called length bias in reward models. These models often tend to just favor longer responses regardless of the actual quality.
Ah, okay. Longer isn't always better.
Exactly. So by including chunks as short as a single token, they teach the reward model to evaluate really fine-grained differences at a very granular level, not just the overall length.
It's like teaching a critic to judge individual sentences, or even words, not just the whole essay.
That's a great analogy. It makes the reward model a much more perceptive judge, not just a length counter.
So it's about making it truly discerning.
Precisely. This variable chunking also means the model is versatile, balancing both token level and sequence level evaluation. And they also do things like randomize temperature and top parameters during generation.
To get more diverse data.
Exactly. Enhances dataset diversity, which is crucial for robust training. Then the training process uses these paired comparisons, cloud LLM output as chosen, SLM as rejected. The goal is always to achieve lower preference loss.
Which means the reward model is getting better at telling the difference.
Right. Better judgment, which translates directly to more accurate routing decisions in the hybrid system. Now, it's worth mentioning this whole system builds on an existing concept, something called speculative decoding, which was introduced by Leviathan et al. A little while back.
Okay, speculative decoding. How does that relate?
Well, in traditional speculative decoding, you have a smaller, faster model suggest a whole draft of tokens, maybe several words ahead. Then a larger, slower model verifies them all at once. It's like a proofreader checking many words in one go to save time compared to checking word by word.
Okay, batch verification.
Right. This paper integrates that idea. The SLM acts as the fast candidate generator, proposing tokens, but then they add this intelligent reward model layer.
Ah, the quality check.
Exactly. To decide if that proposal is actually good enough or if the big gun, the LLM, is truly needed for the next word.
So walk us through what happens at the individual token level then. How does this reward model actually make that real-time decision? Let's say the SLM has just produced a word. What happens next?
Great question. So the SLM proposes a token. That proposed token, along with its context, immediately gets fed into the reward model for evaluation.
Okay.
Now, if the reward model gives the SLM's token a score above a predefined threshold,
The quality bar.
exactly, then that token is accepted. Great. The SLM continues generating the next token locally, fast and cheap.
But if it doesn't meet the bar?
Right. If that score falls below the threshold, it basically means the reward model believes the SLM's output isn't good enough at that specific moment.
Not confident.
So the SLM's token is rejected, and that's when the cloud LLM steps in to generate the next token instead. That ensures the quality stays high.
That's truly dynamic. It really is deciding word by word, and it sounds like this threshold is the key control knob here. Can I really adjust that dial myself?
Absolutely. This is where that fine-grained control we talked about really comes into play. This threshold is dynamically adjustable by you, the user or developer.
So I can tweak it.
Yep. You can raise it if you need higher precision. That means stricter criteria for the SLM and therefore more cloud LLM involvement.
More accuracy, potentially more cost.
Right. Or you can lower the threshold for greater cost efficiency, allowing the SLM to do more of the heavy lifting, maybe sacrificing a tiny bit of accuracy for speed and savings.
It's truly a dial you can turn based on your specific needs.
Yeah.
Maybe prioritize absolute accuracy for one task or maximum cost savings and speed for another.
Exactly. You tailor it to the application.
Now, putting this hybrid approach to the test, the researchers used the Qwen2 family of models for their experiments, right?
That's right. They had the Qwen2 0.5b instruct as the reward model, the small judge.
Okay.
Then the Qwen2 1.5b instruct as the SLM, the local worker. And the Qwen2 7b instruct as the big cloud LLM, the expert consultant.
And you mentioned their reward model training showed low preference loss.
Yes, which was great news. It indicated strong alignment between the reward model and the LLM, meaning it was good at differentiating token quality.
So the judge was well trained. What did the actual numbers tell us about this delicate dance between quality, cost, and speed you mentioned earlier?
Yeah, if we connect this to the bigger picture, the experiments really do illustrate that delicate dance. What they found was a clear correlation. The reward threshold directly influences cloud LLM activation.
Makes sense. Higher bar means more calls for help.
Exactly. A higher threshold means stricter SLM criteria, leading to increased cloud LLM usage. For example, on the GSM-8K math reasoning dataset, a threshold of 1.0 led to about 56% cloud activation.
So just over half the time the LLM stepped in.
Right, but when they pushed that threshold up to 4.0, a much stricter bar, it jumped to 87% cloud activation.
Wow, a big jump. Mostly LLM at that point.
Pretty much. And they saw a similar trend on the MBPP code generation dataset. It went from 35% cloud activation at a 1.0 threshold up to 98% at 4.0.
Okay, so near total LLM involvement at the high threshold there. So
Right.
if you want more of the big LLM, you just raise the bar for the little guy.
Precisely. And conversely, as you'd expect, a higher threshold also means improved accuracy. Why? Because the more powerful cloud LLM is being called upon more frequently.
Right, makes sense. What were the accuracy numbers like?
So back on GSM-8K, the SLM baseline on its own was about 50.7% accuracy. The full LLM hit 77.8%.
Okay.
The hybrid approach. At that 1.0 threshold, it achieved 66.48% accuracy, a nice boost over the SLM.
Better, but not LLM level.
But when they cranked the threshold to 4.0, the accuracy climbed impressively to 77.78%.
Whoa! Almost identical to the full LLM baseline.
Exactly. Closely approximating the LLM's performance, but potentially still saving some cost compared to running the LLM 100% of the time.
That's the trade-off in action.
Yep. And even on the MMLU dataset, that's a broad benchmark covering lots of academic tasks, they found high cloud activation, around 92% even at a 1.0 threshold.
Okay.
Led to an accuracy of 69.9%, which is very close to the full LLM's 70.5%.
So in some cases, even a modest threshold triggers a lot of LLM help if the task is hard.
Right. But there's always a but. This higher accuracy comes at a cost, specifically in terms of throughput or speed.
Ah, okay. Because calling the cloud LLM takes longer.
Exactly. Relying more on the cloud LLM, which inherently has higher computational costs and longer latency, naturally decreases the overall processing speed.
Makes sense. Got any numbers on that?
Yeah, for instance, for that MBPP code generation task, throughput dropped from about 6.4 tokens per second at a threshold of 1.0 down to 4.1 tokens per second at a threshold of 4.0.
So slower speed as the accuracy went up.
Right, because cloud activation rose from 35% up to 98%. It's like Choosing between a super fast bike courier for a small, simple package versus waiting for a complex, highly secure armored truck shipment?
Yeah. Both get the job done, but at very different speeds and costs.
Exactly. And the CN-NDM summarization example also showed this. Even at a relatively low 1.0 threshold, they still saw significant cloud activation, about 59%. And that reduced throughput significantly, down to like 4.8 tokens per second compared to the SLM baseline, which was way faster at almost 24 tokens per second.
So you're essentially picking your poison, right? Or maybe picking your priority. More cloud calls for higher accuracy, but slower speed, or more SLM usage for better speed and lower cost, potentially sacrificing some top-end accuracy.
That's the core idea. It's all about finding that sweet spot for your specific need.
And this system lets you dial it in with surprising precision.
That's the promise. Now, while this architecture offers significant advantages, it's not perfect. The researchers acknowledge a few limitations.
Okay, what are the main ones?
Well, first, that reward model alignment is crucial. If its judgment is flawed, if it's not really capturing the LLM's distribution well, it can lead to either suboptimal quality, not calling the LLM when it should, or unnecessary cloud costs, calling it too often.
Tricky balance.
And also, this reward model needs recalibration for every new SLM-LLM pair you want to use together.
So setting up a new combo takes effort.
It can be quite resource intensive, yeah. Then there's also inference time overhead.
Meaning the reward model itself takes time to run.
Exactly. It adds a small amount of latency per token check. Especially if many SLM tokens get rejected, that could potentially increase the total inference time compared to just running the SLM alone.
Okay.
Then there are potential scalability concerns, like managing lots of different reward models for many different SLM-LLM pairs could get complex in a large system.
Right, keeping track of all those specialized judges.
And finally, threshold tuning itself is an ongoing challenge. Finding that truly optimal threshold for every situation. It likely requires continuous adjustments and experimentation. It's not set and forget.
Okay, so some practical hurdles remain. But this isn't the end of the story, right? The researchers have some exciting ideas for what comes next for this promising technology, what's on their roadmap.
Absolutely. They envision several potential improvements down the line. One idea is implementing cache mechanisms.
Caching, like remembering previous answers.
Sort of. Storing previously accepted LLM tokens to reduce redundant cloud calls if the same sequence comes up again. They suggest this could even be enhanced with things like look-ahead decoding, where the SLM speculatively generates multiple tokens ahead.
Interesting. What else?
Another technical improvement would be introducing a KV cache for the LLM.
KV cache. That rings a bell.
Yeah.
It helps with long sequences.
Exactly. It's a smart way to store parts of previous computations, specifically the attention keys and values in the transformer model. It essentially lets the model remember what it has already thought about, which significantly speeds up generating long sequences because you don't have to recompute everything from scratch each time.
Makes sense for efficiency.
Then they also suggest improving the reward model itself, maybe through more sophisticated training techniques, better optimization, or perhaps incorporating ideas like grounding sequence-level preferences down into token-level guidance, making the judge even smarter.
And what about that threshold? You said tuning it is hard?
Right. So a very compelling idea is dynamic reward threshold adjustment. Imagine the threshold adjusting on the fly.
Oh, automatically?
Potentially, yeah. Based on context, maybe the model's own confidence level, or even the type of task it's performing. That could lead to even more flexible and efficient routing without constant manual tweaking.
That sounds powerful.
They also talk about improving LLM alignment, basically.
Yeah.
Training the smaller model to think more like the bigger one from the get-go.
So the SLM would get more tokens accepted.
That's the idea. Increase accepted tokens, reduce the need for LLM assistance, improving efficiency further. And finally, they mention multi-model collaboration.
Like more than just one SLM.
Yeah, exploring scenarios where maybe different specialized SLMs could work together with the cloud LLM, forming an even more adaptive and capable system. Lots of interesting directions.
Definitely sounds like there's room to grow. So wrapping this up, what does this all mean for the bigger picture? This research, it really introduces a truly novel way to get high-quality language model output without those often prohibitive costs, doesn't it?
I think so.
Especially when you need that fine-tuned balance between speed, cost, and quality. The core innovation really seems to be that per-token routing and the dynamic control it offers.
Yeah, it lets you fine-tune the balance between efficiency and performance precisely for your needs.
Which is huge.
I agree. This work significantly reduces reliance on those expensive cloud LLMs while still maintaining competitive accuracy across a range of different tasks. It really opens up new possibilities for efficient language model inference, particularly in situations where resources are limited or maybe cost is just a major factor. It makes advanced AI potentially more accessible and applicable in a much wider range of scenarios.
And this idea of per-token intelligence. You know, an AI making a judgment call on every single word it generates. That isn't just about saving money, is it? Think about what this level of granular control could mean for how you interact with AI. Imagine personalized creative writing assistants that only call on the, master poet LLM when they're truly stuck. Or super efficient coding tools that adapt their intelligence to your needs in real time, only bringing in the heavy artillery for the absolute trickiest bugs. What possibilities does this spark for you as AI becomes not just powerful, but also exquisitely adaptive?